What if I told you that the Sun, our nearest star, doesn't rotate like a solid spinning ball? Instead, it performs one of the most mind-bending cosmic dances in our solar system, spinning faster at its equator than at its poles. This phenomenon, called solar differential rotation, is reshaping our understanding of stellar behavior and space weather. Imagine trying to spin a jar of honey. The honey near the center moves differently than the honey at the edges. That's exactly what's happening with our Sun, except on a scale so massive that it defies our everyday experience. The Sun's equator completes one full rotation in about 25 days, while its poles take a leisurely 35 days to make the same journey. This isn't just a quirky cosmic fact. Solar differential rotation is the engine behind some of the most spectacular and dangerous phenomena in our solar system. It's the reason we have sunspots, solar flares, and the beautiful yet potentially destructive aurora that dance across our skies. To understand why this happens, we need to think about what the Sun actually is. Unlike Earth, which is mostly solid rock with a thin atmosphere, the Sun is a massive ball of plasma, a fourth state of matter where electrons are stripped from atoms. This plasma behaves more like a fluid than a solid, allowing different parts to move at different speeds. The Sun's differential rotation was first discovered in the early 1600s by Galileo Galilei, who observed sunspots moving across the solar surface. He noticed that spots near the equator moved faster than those near the poles. For centuries, astronomers could only observe this phenomenon at the Sun's surface. But modern technology has revealed the incredible complexity hidden beneath. Using a technique called helioseismology, scientists can now peer inside the Sun by studying how sound waves travel through its layers. Think of it like using ultrasound to see inside a human body. But instead of looking at organs, we're mapping the Sun's internal rotation patterns. What they discovered was revolutionary. The Sun's differential rotation extends deep into its interior, creating a complex three-dimensional pattern that would make any engineer's head spin. The rotation speed changes not just with latitude, but also with depth. Near the surface, the difference between equatorial and polar rotation is most pronounced. But as you go deeper, these differences become less extreme. At about 200,000 kilometers below the surface, there's a boundary layer called the tachocline. This is where the Sun's radiative zone, which rotates almost like a solid body, meets the convective zone above it, which shows strong differential rotation. The tachocline is only about 5,000 kilometers thick, incredibly thin compared to the Sun's 1.4 million kilometer diameter. This boundary layer is crucial because it's where the Sun's magnetic field is generated. The differential rotation acts like a cosmic dynamo, stretching and twisting magnetic field lines until they become incredibly complex and powerful. These twisted magnetic fields eventually break through the Sun's surface, creating the dark patches we call sunspots. Sunspots aren't just cosmetic blemishes on our star. They're magnetic powerhouses that can be larger than Earth itself. The most active sunspot regions can contain magnetic fields 10,000 times stronger than Earth's magnetic field. When these magnetic field lines suddenly reconnect and release their stored energy, they create solar flares that can release more energy in minutes than humanity uses in an entire year. The Sun's differential rotation follows an 11-year cycle that directly affects space weather and life on Earth. During solar maximum, when the Sun's magnetic field is most twisted and complex, we see increased solar activity. Solar minimum periods are relatively calm, with fewer sunspots and less dramatic space weather. But here's where it gets really interesting. Recent research has revealed that the Sun's differential rotation isn't constant. It varies over time, and these variations can affect the timing and intensity of solar cycles. Some scientists believe that understanding these variations could help us predict space weather more accurately. Space weather might sound harmless, but it's anything but. When the sun releases a massive solar flare or coronal mass ejection, it sends billions of tons of charged particles racing toward Earth at speeds up to 3,000 kilometers per second. These particles can disrupt satellite communications, damage power grids, and even pose radiation risks to astronauts and airline passengers. The 1859 Carrington event, the most powerful geomagnetic storm in recorded history, was caused by a massive solar flare. Telegraph systems worldwide failed, with some operators receiving electric shocks. Aurora were visible as far south as the Caribbean. If a similar event occurred today, it could cause trillions of dollars in damage to our technology-dependent civilization. Differential rotation isn't unique to our sun. Other stars show similar patterns, but with fascinating variations. Fast-rotating stars can have even more extreme differential rotation, while some stars rotate so slowly that the differences are barely detectable. Binary stars, where two stars orbit each other, can have their rotation patterns influenced by their companion's gravitational pull. Scientists are using computer simulations to model stellar differential rotation, trying to understand how factors like stellar mass, age, and composition affect rotation patterns. These models are incredibly complex, requiring some of the world's most powerful supercomputers to solve the equations governing fluid dynamics, magnetic fields, and energy transport. The implications extend far beyond our solar system. Differential rotation affects how stars generate magnetic fields, which in turn influences their habitability zones and the potential for life around them. Stars with more active magnetic fields might create more hostile environments for planets, while others might provide more stable conditions for life to develop. Recent missions like the Parker Solar Probe and Solar Orbiter are providing unprecedented insights into solar differential rotation. Parker's Solar Probe has flown closer to the Sun than any previous spacecraft, measuring the solar wind and magnetic fields with incredible precision. Solar Orbiter is giving us our first detailed views of the Sun's polar regions, areas that are crucial for understanding global rotation patterns. One of the most surprising discoveries is that the Sun's surface rotation can change over short timescales. During solar flares, the rotation speed can temporarily increase in localized regions. This suggests that the Sun's rotation is more dynamic and responsive than previously thought. The study of solar differential rotation is also revealing connections to climate change on Earth. Solar activity variations can influence Earth's climate over long timescales, and understanding these connections requires detailed knowledge of how the Sun's rotation affects its energy output. Future space missions will continue to unravel the mysteries of solar differential rotation. Proposed missions include solar probes that could orbit the Sun's poles, giving us three-dimensional views of rotation patterns. Advanced instruments will measure rotation speeds with unprecedented accuracy, helping us understand how differential rotation varies across different types of stars. As we prepare for human missions to Mars and beyond, understanding solar differential rotation becomes even more critical. Astronauts on long-duration missions will need accurate space weather forecasts to protect them from radiation. The key to better forecasts lies in understanding how the Sun's complex rotation patterns drive space weather. The Sun's differential rotation reminds us that even our closest star holds secrets that continue to amaze and challenge us. Every day, this cosmic dance of plasma and magnetic fields influences our technology, our climate, and our understanding of the universe. What other stellar secrets are waiting to be discovered as we continue exploring the cosmos around us? Thank you for watching. Please like and subscribe to support us.